Today we're going to talk about two relatively, I would say, obscure features of the Haskell language, the monomorphism restriction and defaulting. And in my experience, these are features that typically when you learn Haskell, you run into this a couple of times and you get confused. And then you forget about it, basically, for many, many years. And like the funny effect is that, like I was just talking to Etzke about this before the episode, that sometimes even when you have been doing Haskell for many, many years, you have actually not like a very good understanding or systematic understanding of what these things even do. You have an intuitive way of making it work, but yeah, as I said, they're so obscure. So today we are actually going to try to dive into this. We are going to look at a couple of examples and try to understand what it means and why the designers of Haskell may have thought that this is possibly a good idea.
Yeah, so welcome to the Haskell Unfolder, a YouTube series where we discuss all things Haskell. As always, the show is live streamed, so we invite you to submit questions or comments in the chat, and we will try to show them on screen and discuss them. And I'm looking forward to learning something new today, because I am definitely one of those people that has spent many years on Haskell without ever thinking about this. So, yeah.
Yeah, okay, so let's start with a simple example. Let's check whether in a given list, like a list of strings, there is an empty string. So we write something like elem empty string in a list of strings, let's say foo bar, something like that, right? That is a Boolean expression. And we can evaluate it. And it evaluates to false. If I would actually put an empty string in here, then it should evaluate to true. So far, so good. So now, assume that we want to test whether the empty string is contained in something all over the place, and we want to give a better name to our function, right? And so we could say, like, we want to say something like contains empty, right? And just define it as the partial application of elem to the empty string. Now, surprisingly, perhaps, this partial application suddenly doesn't type check. We get a type error for this. And actually, like, I'm having HLS enabled, and I'm getting this error message displayed here. I also get an infer type, and the infer type is really weird because
it's very strange.
Any, right?
Yeah.
But let's first look at the error message. The error message actually says that there is an ambiguous type variable T0 arising from a use of elem, and that prevents a constraint foldable T0 from being solved. So that is interesting. So let's first of all remind ourselves what's actually the type of elem. For Haskellers that use Haskell for a very long time, this still feels unusual, but elem, since a long while actually, has a foldable constraint. It's not actually a function on lists, right? So it is it's a member of the foldable class, I think, or it's defined in terms of foldable. I think it's actually a member of the foldable class, but I'm not 100% sure right now. In any case, it has a foldable T constraint and EQ A constraint. And it takes an element and a structure of A's and it returns a Boolean, right? And if we apply it to a string is a list of characters, then that should be fine. And indeed, if we just ask explicitly what is the type of elem to a list of strings, GHC will reply and say, well, then you have to give me a T of strings, and T should be foldable, and that returns a bool. And that's exactly what we have written here. And so if we now say, why, GHC, why are you so stupid? Why are you not just doing this? And we give the type signature, then suddenly everything is okay, right? So like this is weird, right? And this is the so-called monomorphism restriction in action. The monomorphism restriction is a situation in which, like, even though type inference would allow us to give sort of a particular type, GHC refuses to actually assign that type to a definition and complains about it.
We could have done an error message here.
The error message is not that great. I mean, so it is actually correct, but I really wish it would actually mention the monomorphism.
Yes,
right?
exactly.
Because it is that would really help, right? And also, I mean, I'm sorry, I usually don't really want to criticize GHC very much because I think it is very, very cool. So for example, these error codes are very, very cool, but I looked up in preparation for this episode, I briefly looked whether I could like proudly point to the Haskell error messages index and say that it has a very good explanation. But not only does the error messages index, which generally is a fantastic effort, not have a great explanation for us, it seems to be even worse. It seems like GHC-39999 is sort of a catch-all error code for all sorts of type class related errors that not just cover this case, but also a couple of other cases. And so that makes it like even harder, right? So
scope for improvement.
Yeah, there is room for improvement here. So, but what is the monomorphism restriction saying exactly? So it's saying that a binding, right? This is a binding. A binding is such a declaration which has an equals, effectively. A binding that syntactically does not have arguments, like does not have function arguments to the left of the equals, right? So this contains a single identifier to the left of the equals, and there are no syntactic arguments, even though on the right-hand side we have a thing which is still a function type, right? But it is not syntactically having arguments here on the left-hand side. Such a binding cannot have an overloaded type.
And just to be clear, we're only talking about top-level bindings here.
No.
Okay.
So if I do f equals let contains empty in whatever, I get the same error.
Okay. And is this also true for a where clause? Just, I mean, since
I mean, this is a legitimate question, and even like
it is a genuine question.
I was embarrassingly confused about this myself, apparently, because another thing that I did in preparation for this episode, I rewatched my own video, which I recorded a couple of years ago for the sort of like introductory Haskell course on the same topic, and there I mistakenly also claimed that this is only true for top-level bindings. In principle, from my current perspective, I knew for a long time that this is not the case. But apparently, I was confused at the time when I recorded this video. But apart from that, there is also a course that you can watch if you want to learn more about Haskell in general. It's publicly available, right? And it also has an episode on this, which is not completely identical to this. It contains this one mistake, but is otherwise still an interesting episode. So it's not a where clause. You asked about a where clause. Let's do this as well. So to just have the complete picture. Okay. So it applies to bindings, right? It applies to bindings that have that don't look like. Okay, so they must not look like functions in the sense that they must not have explicit arguments on the left-hand side, and they must not have an explicit type signature, right? So if you give an explicit type signature, then the problem disappears, right? That's what we saw if we go back to this. If we actually add a type signature, contains empty, foldable. I mean, it can be the overloaded type signature, or it can be a more concrete type signature, right? Obviously, both is fine. If we say this is actually supposed to only work on a list of strings, that's also fine. And the other way to make it go away is to, for example, actually, that's not an option you always have, of course, because it's not necessarily a function, but in this case, it is a function, right? So we could actually give an argument explicitly and give the argument on the right-hand side, like to eta expand the function. And then we can even remove the type signature, and it infers the type just fine, right? And then we can insert it again. So that's the monomorphism restriction, okay? And Yeah, so sometimes.
So what is the restriction? You talked about when it applies, but what precisely is the restriction?
Oh, the restriction is that this such a binding cannot have an overloaded type. So an overloaded type meaning a type that has any constraints, any type class constraints.
Right.
And a polymorphic type is fine, right? That's very important. Like I can say foo equals ID, and that is inferred to be a monomorphic type. But if I say something like foo equals, oh, that's monomorphism restriction because double equals is an overloaded thing, and it doesn't work. And again, like the two options are either give arguments, right? Then it goes away, or give a type signature. Now, what's the reason for this? I mean, and I think that the reason is that if you look at the translation of an overloaded function, right, then an overloaded function is translated into a function that takes an extra argument for every type class constraint that it has, right? So if we can even do that. I mean, we can like perhaps remove example contains empty. Let me just quit the editor and let's do a GHC dedump simple desuppress all no typable binds.
So just show us the core things without all the extra bits that distract, basically.
Yeah, so exactly. So basically we want to see the core output of the monomorphism restriction module. And you can see here that contains empty. Like this is a type argument, so you could perhaps hope that the type argument actually disappears later on, right? So that is perhaps questionable. But this thing here is a real argument, even though it has a weird syntax. But this is sort of the foldable dictionary, right? It's like a record with the implementation of the foldable class for the type that we're actually calling the function on in the end. So if we assume we're calling it on a list, it would be the foldable dictionary for lists, which contains the implementation of all the methods of the foldable class for lists, which can then be extracted from the dictionary. Like LM is then actually like a record selection from this dictionary, which selects the thing, right? And so this is actually an argument that is being passed. And now, why is that potentially problematic? That is because we typically expect in Haskell that if we have bindings, let bindings, but also top-level bindings in both cases, that they are shared, right? And in particular, shared in such a way that if there are constants, right, if they don't have any arguments, we expect them to be evaluated at most once, right? And that's great, right? But if a binding that looks to the user, to the careless user, let's say, but nevertheless to the user like a constant, and the user may sort of assume that therefore, this will be evaluated only once, but it is actually overloaded, right? Then that assumption is wrong, and we can try to demonstrate this, right? So there is actually a way to disable the monomorphism restriction. So you can sort of basically, this is a language extension which is, oh yeah, you have to spell it correctly, otherwise it won't work. But it's a language extension that's actually enabled by default, but you can explicitly disable it, right? So no monomorphism, that's the way GHC looks at it. You can disable it with no monomorphism restriction. And then, right, I can suddenly do this kind of stuff. And it just works. It still works, like no error, right? So really fine. But now let's do something like this. Let me write a naive, expensive Fibonacci function. Let's do Fibonacci 0 is 0, Fibonacci 1 is 1, Fibonacci n is n minus 1, just to have an expensive computation. So this has a sort of relatively overloaded type. And then let me say something like I write a function test that takes a Boolean, and then I do something like, oh, do I even want this? Perhaps I only want to. No, let me just do something simpler. Let me define a top-level constant that says something like I want to evaluate fib29, and then I simply say my test is now, let's say, an integer specifically, and I want to call k plus. Well, let's first of all just call k, and let's see what test evaluates to. And this has a little delay, so this is more than I want. Let me calibrate this a bit. Let's say, yeah, so this has a very short delay, but a noticeable delay, right? So if I evaluate this, let's remove this once more. If I evaluate this, it's not instantaneous, but it's noticeable. And now if I do something like this, right, and then re-evaluate, we would expect this is equally fast, right? Because fib27 is a constant, right? I mean, ideally we would expect it to be. Now with everything I said already, it's perhaps no longer surprising, but ideally we would expect fib27 to be calculated once and then be reused a couple of times, and we would basically expect the delay of this call to test be exactly the same as the delay that we experienced for this single k. But it isn't, and that is because k is a function, right? Because k is of type num a double arrow a now that we have disabled the monomorphism restriction. And that means that even though this looks like it's a constant, right, it is actually something which is receiving the num a dictionary every time we're calling it. Now, if you compile this particular program with optimizations, then GHC might in this case still be able to figure out that we're actually using this at a particular type and optimize it all away because it's so simple. But it's not something you can rely on, right? And it makes things suddenly relatively fragile.
And so just to be clear, test itself is just a regular integer. It would only be evaluated once. And if we have test2 equals test plus test plus test plus test, it would definitely, test would be evaluated precisely once. But because k is overloaded, every time that we call it, it's a function call and we recompute it.
Yeah. And this even happens if you do this sort of in a setting like this, right? Because if we look at the type of k here, this is you don't get it printed as nicely by HLS, but it is, you can see it's still an overloaded thing, right? Because let is generalized by default in Haskell. There's actually something that is changing, and this is something perhaps we can talk about it very briefly and at the very end, but I still have other things to go about. So basically, more recent GHCs changed the generalization behavior, but the standard Haskell behavior is to generalize every let. And so basically this will get the overloaded type. And this version of test will still be, should still be slow. Oh no, this one is, okay, so perhaps so here I'm surprising myself, but why I'm getting a here?
Are you sure that it's actually fast? I mean, you're okay. Are you able to precisely enough?
Yeah. That's interesting. Perhaps I should look at the code generated by test again. Wait, I should not remove fib. So it's okay. So there's inlining even without No, but still. No, it's still having several calls to fib.
Or you don't know what the evaluator is doing, right? I mean, the code evaluator might do something clever.
I mean, so at the very least, you can even see from this core output that there are like seemingly multiple calls to fib rather than one shared call, right? I mean, I'm slightly surprised that we are observing relatively fast behavior, perhaps. I mean, let me see it. No, it's actually not fast in here. So perhaps there is something.
Yeah,
perhaps there is something with the I don't know, with the eval plugin, some interaction. Perhaps it was sharing the result of test itself.
Yeah, that's what I pointed out earlier.
Yeah.
Every evaluation of test.
Yeah.
Evaluated, you get the same.
Yeah. I think that was what was happening. Okay.
Yeah. So one thing in particular is, if you go back to the example here, is that the type of K here is again a polymorphic type, even though we know that we want this to be an integer. Right? It's the type invert for K is not integer. It's for all.
Well, I mean, so this is the next thing we're getting to, right? So I mean, if we re-enable the monomorphism restriction for the time being, and we now look at this example test, then we actually see that for this situation, we're not getting an error, right? Even though we've just seen this also has an overloaded type, and the monomorphism restriction should apply, and then in fact it does apply. But now there is another language feature that is coming into play, which is called defaulting. And that means that in this particular case, yes. Yeah.
Okay, I'll let you finish first, and then I'll ask.
But in this particular case, we actually get the type of K to be integer.
But this is because actually not because of the signature for test.
This is because of defaulting, not because of the type signature for test. Yeah.
So if you change on line 22, you test it to be float, we get a type error again?
No.
But the defaulting?
That's different because, I mean, oh, actually, yeah, so you're right. I mean, in this particular case, you can argue that it's both. I mean, or perhaps that is even the type signature is enough. Yeah, you're right. I mean, you're right. I'm wrong. I mean, because in this particular case, we are the fact that the monomorphism restriction applies is enough, right? I mean, we know we want a monomorphic type, and we know that it's used as something which in the end must be an integer. So therefore, the monomorphic type must be integer. You're right. But if we go back to the situation where this was global, we still get integer.
This is different.
Yeah, this is different, right? And also, if we
now fix integer,
if we were just not using K at all here, then it would still be integer.
Right.
Right. That's also this, right?
Even if we give, so if you now change test to be float, just to be absolutely.
Yeah. Now the
K is still integer.
Now the K is still integer.
Yeah. Yeah. Okay.
And that is defaulting. So and so defaulting exists independently of the monomorphism restriction, but in particular in the context of the monomorphism restriction, these two interact, right? Because in situations such as these bindings here, we have a situation where we cannot use an overloaded type, and we have to choose one. And defaulting says that under particular circumstances, we can make a choice. And the way that Haskell specifies this is very ad hoc and very arbitrary. So basically, the only place in classic Haskell where defaulting applies is for numeric classes, right? And basically for num, fractional, these kinds of classes. And the types that it will try to default to by default, are integer, if possible, right? That's what we are seeing here. That integer, not int, integer. And if integer is not possible, it will try double. Right, so that means in particular, if I define something like 2 equals 2, that will get type integer. If I define 2.5 equals 2.5, that'll get double because it can't be integer. Right?
Mm-hmm.
That's what it does. It doesn't work for any other classes. You cannot default other class, like you cannot.
So there contains empty nothing. There's no defaulting that would save you there.
Exactly. For contains empty, there's no. That's why I started with that, because it's really something which is not tied to defaulting at all. And there's also no. I mean, well, actually, we can talk about that as well. But I mean, in classic Haskell, there is no way of making defaulting work for that. There is a way to, weirdly enough, there's a way to configure defaulting, right? And it's there's a top-level declaration you can use in a Haskell module that tells what defaulting you want to apply in that module, and that's a default keyword. And this is so obscure that, like, I mean, my syntax highlighter doesn't even recognize it as a keyword, funnily enough. So, and the syntax is that default is a keyword, and you basically put within parentheses, you put the types you want to default to, in which order. So basically, the normal behavior of Haskell corresponds to this default declaration.
Yeah, so when Andrew showed me this just before the episode, what is really confusing to me is that you don't actually say what to do. Like, what are you defaulting? Which class?
That's because the default construct is just like very ad hoc, and it is just working for these numeric classes in the first place. And you're basically only saying, try these types in order if you are in such a situation. And so basically, if we say only double, just for fun, then suddenly my k becomes a double as well, right? And my 2 becomes a double as well. And if I put an empty list, then defaulting is off. Then all these things become type errors again, right?
This is also possible. Can I turn off the defaulting for my project? Is there a language extension that does the same thing?
I don't think so. Although if somebody from the audience knows that there in fact is, then I'm happy to be educated. But I don't think so. I think you can like make defaulting even more general. There is a language extension, extended defaulting rules, that makes it more general, which I'll just mention in a moment. But I don't think you can globally disable it. You can disable it per module.
Okay.
Not sure. Yeah. So this is fun. It's another thing, perhaps another like sort of curious corner case is that, like, I mean, the rules, if you're really interested in the nitty-gritty details, right, they're all specified in the Haskell report. Like the Haskell 2010 report, there's section 455, which talks about the monomorphism restriction. This is actually like phrased in a really complicated way because there are things such as pattern bindings, right? And how does it interact with pattern bindings, and what does actually count as having a type signature and what does not count as having a type signature? But the essence is what I said, right? And then in 434 there is defaults for overloaded numeric operations being specified, right? One thing that is interesting is that if there are additional type class constraints, then defaulting can also be off potentially. So if we define a user-defined class, like say num a arrow double arrow foo a, so which has num as a superclass, and we just say foo is a value of type a, and we now say 2 plus foo, then suddenly the defaulting is no longer kicking in, because now we have a constraint for foo and for, well, basically for foo, and foo implies num, but foo is not one of a predefined set of, say, whitelisted classes which are allowed to appear in situations where defaulting is actually kicking in. And so basically only sort of prelude classes are allowed effectively. So like EQ, show, read, whatever, in addition to num or these kind of numeric classes. It's really weird, right? But it's a feature that exists. Okay, and yeah, perhaps as a final point, I should say that like in GHCI by default uses no monomorphism restriction actually. So no monomorphism restriction is enabled by default in GHCI, and additionally, in GHCI you also have an extension enabled that is called extended defaulting rules. And why is that? I mean, so the defaulting, apart from this interaction with the monomorphism restriction, right, it also serves practical purposes. A good thing is that in GHCI we can like type 22 and we actually get a result. If we had no defaulting and we had the monomorphism restriction, I'm not actually sure whether this works. Does this work? Yeah, if we had no defaulting, then like typing something like this would already be an ambiguity error, right? And that's really annoying. And indeed, I mean, also this defaulting for numeric types, like in practice, one is often using this, right? If you enable W all, then GHC will actually warn about defaulting being applied, right? So if we go back to integer double and now type something like this, then it will actually warn about this. And if you enable W all, you will see that, I mean, I get that from time to time. There are situations where you get defaulting in day-to-day code that you're writing. A very common example is actually the exponentiation operator, which is like sort of overloaded in both type arguments. And if you're writing something like, yeah, let's say we even have an integer. Let's say we have an like example, or n is int, n is 55, and we want to compute n to the power of 3, right? Then, then like without further type annotations, the 3 is like defaulted, right? And so there, this occurs in practice. So there's a practical reason, and in interaction this is even more pronounced, right? Because there are other situations. What, for example, if we type the empty list, right? The empty list in itself isn't overloaded, but if we want to print it, and GHCI wants to print back all the results of all the evaluations, then you need a show instance. And so it has to decide which show instance to use in order to print the result. So in this particular case, right, it has to use a particular show instance. And now I've actually, by doing default declarations, deviated from the normal GHCI behavior. So the normal GHCI behavior in this case is that it will actually default to unit. And so this is what the extended defaulting rules does. Extended defaulting rules does two things effectively. It increases the set of admissible type classes somewhat. Right? Like I said, like in the classic defaulting rules, you can like only the numeric types are actually defaulted, but additional constraints you can have are very limited. They basically must be prelude classes. With the extended defaulting rules, this is extended to something which I think is called interactive classes, and it contains things like foldable and traversable and like a couple more.
Is that within reach for programmers? Could you do something with this, or is this something like just that's hard coded for GHCI and that's like?
No. You can, but in my personal opinion, you really should not enable extended default rules in actual modules, and you can then also give default statements that apply to this. So you can now do something like, for example, you can say you want foldable to be defaulted to maybe. So basically,
but again, even here we specify no class.
Yeah.
So even here we're not specifying.
No, this is still across all the defaultable classes. Try every type on order.
Oh wow.
So if I do something like this, and now I do what is the now I do something like f equals null. Now the type of f oh, this is because no monomorphism restriction is also active. So if I now enable the monomorphism restriction and then define f again, now we get a defaulting warning, right? Like let's do this for G, and then the type of G is maybe A tuple.
Yeah. Which is maybe a nice segue into an audience question.
Yeah.
Is there a better way to do this? Is it nobody thinking any harder about design decisions like this than the GHC people? Which is somewhat controversial, but
no. I mean, I think it's a valid question in the sense that this is it's totally valid, and I mean it's I think nobody really says this is a beautiful feature. It's like one of the few cases where actually I think Haskell is surprisingly pragmatic, right? And many other cases you can say, oh, well, Haskell goes to endless lengths to make things, I don't know, seemingly complicated when you could just do like 99% of all real world cases with a simple hack. And this is one of the cases where Haskell goes the other way. Like you have a very pragmatic thing which like covers a surprising amount of the useful cases. And basically, it's not sufficiently much of a problem that anybody really wants to, I think, design a better feature because, usually, right? I mean, most of the defaulting, again, you can fix every defaulting by giving an explicit type signature. There are not all that many situations outside of sort of interactive use or ad hoc use where like typing in an extra type signature in such a situation is really asking too much, I would say, right? It's primarily this pragmatic, quick interaction with Haskell programs where this arises really a lot, and where it would be a pain if we would require all these extra things. And I think that's just like, a pragmatic choice. And I think it's not, it isn't bad, but it is a weird corner. You could design a better feature, but would it be worth it, right? I mean, would it be a cost, like a good cost benefit ratio for adding it? I mean, I don't think it is particularly difficult even to because I mean the theory of defaulting is not that hard to understand, but is it the use of defaulting might become harder to understand, right? If you would actually make it fully configurable and have a fully configurable feature for all classes, and you could enable defaulting for user-defined classes, you would have one more thing, which is actually different all the time in every module, for every library, for everything, which perhaps also creates overhead that you don't actually want, right? So, the defaulting to unit, as perhaps the final thing I want to say, is a pitfall, right? I mean, I think I've mentioned this once in another episode. So in particular in the context of quick check. Let me go back, make sure that I have like sort of the standard GHCI setting. So you can define like say a property that checks whether a list is equal to its reverse, and then quick check that property. Not prop. Yeah. And it says, fine, right? And again, like, why is that? Because if we look at what happens here, it's defaulting the element type of the list to unit. Yep. And that's not what you want in this case. So be a little bit careful. In particular, I think this is the main place where I've been running into this. If you're using quick check with GHCI and in that combination, then be careful about the defaulting, right? Because like really here, you don't want to test this on the unit type. You want to test this sort of like on int or something like that.
I don't think it has a polymorphic type. Maybe. No, it doesn't.
No, but prop.
Oh.
No, I think it's just that type applications isn't enabled. Is that it? Oh no, what is the problem? Prop at int? No, cannot apply expression to divisible. Oh, because I haven't given a type signature. I think that's.
Oh, really?
Yeah, I think, is that it? EQA.
That's fair enough.
Yeah, then it works.
Oh,
yeah.
Okay. Fair enough.
And then you get a counterexample.
Reassuringly.
Yeah. Yeah, I think the reasoning, this is like sort of out of scope for this episode, but the reasoning is that if you have if you don't have an explicit type signature, you don't know the order of
Sure.
The type arguments. You haven't documented the order of the type arguments. And if you give an explicit type signature, there is kind of a rule for how this is being.
Even though you didn't specify an order.
Yeah, it is. It's like, I mean, it is allowed.
On
It is allowed to do this without explicit quantification, and it's kind of the order in which they appear in this signature. But I mean, you can of course use explicit quantification, which is even better. Yeah. Okay. Let's leave it at that.
Yeah. Thanks everybody for watching this episode of the Haskell Unfolder. If you enjoyed it, please like and subscribe. We'll leave the chat open for a few more minutes if there's any more questions. Otherwise, feel free to leave comments below the video, and we always try our best to answer all of them. And hope to see you again very soon, probably 2 weeks, but we're not entirely sure yet. But soon.
Okay. Bye-bye.